We're going to go through an elucidation question. This is from Arene's workbook, structured question 21. So before we start, can you just change a phrasing over here? We are going to change the word geometric to cis-trans because this is the term that we use in the current syllabus. Okay, so this elucidation questions has several unknown species labeled from A to F, and they have given you some reactions that these unknown species undergo, and you're supposed to find out what is the exact identity following the hints that they have provided in the question. So just like any elucidation question, you should construct a table, which I've done so beforehand. Okay, so this is what I have, and the table is classified with two columns, one which is on evidence, the other one is on deductions. Okay, and just a reminder, a deduction actually mean that you need to include several things possibly, which includes functional group, okay, type of reactions, okay, and in some cases you would probably need to know the specific structures. Okay, an example of specific structures could mean terminal alkenes in what we have learned in alkenes, okay, when it undergoes oxidation. Okay, so I've listed the different statements in the question, and that is shown on the left column on evidence. Okay, so if you were to look at the question itself, it started off with saying that a hydrocarbon A has the molecular formula of C10H14, and that is the first evidence that I have over here. And from this statement itself, you should be able to tell that it gives us some hint about the functional group because of the fact that the carbon is to hydrogen ratio is approximately 1:1. Not exactly 1:1, but this would be a good hint to tell us that when this happens, it indicates that a benzene ring is present. Okay, and then we move on the line. What else it also mentioned is that when A is treated with hot aqueous KMNO4, okay, benzoic acid is present. So I'm at the second line itself. Okay, and now what happens is that I can actually deduce certain things as well. With the use of hot aqueous acidified KMNO4, I can deduce the reaction, okay, which is the fact that it is an oxidation process. So I will mention that A undergoes oxidation. Okay, and since it forms a benzoic acid, you need to have an idea that a benzoic acid looks like this. Recall what you have learned about the products that can form benzoic acid. It typically refers to any benzene that has a benzylic hydrogen. And because benzene has 6 carbons, but in hydrocarbon A, it actually has 10, it means that out of the benzene ring, there are actually 4 other carbons. Given that the product is benzoic acid, which means that only one side of the benzene ring is substituted, it tells you that the extra 4 carbons out of the benzene ring, it's situated on 1 carbon of the benzene ring. So in this case, the deduction that you can make is that A has only 1 alkyl side chain. Okay, what this means is this, okay, if compound A has a side chain of R, where R has a benzylic hydrogen, regardless of how long this R will be, okay, upon oxidation, This R with the benzylic hydrogen would just convert itself to benzoic acid. Okay, so this is what we meant. The reason is because if there's more than one side chain, so example, if there are two, in this case, with side chain oxidation, if both groups has benzylic hydrogen, instead of a benzoic acid, it would form a dicarboxylic acid because both sides would be substituted. Okay, so because this question is talking about benzoic acid being formed, this is what we are looking at, and therefore it has only one alkyl side chain that we can deduce. Okay, moving on, the next line is that when reacted with bromine in the presence of UV light, A produced 4 isomeric monobromo compounds with the formula C10H13Br. And if we were to do a comparison between the formula of A as well as the product of C10H13Br, they are a difference of 1H and 1Br. Okay, so that gives us a hint as well. So before that, let's just look at the type of reaction based on the reagents and conditions, which you should be able to tell that with this, A actually undergoes free radical substitution. Okay, because of the UV light. And since it forms 4 isomeric monobromo compounds with the molecular formula of C10H13Br, it gives us a hint that the hydrogens on the side chain actually is different types, meaning that when the hydrogens are being substituted, they give different products. Okay, so actually at this point in time, you can actually kind of have an idea of what is a possible reaction. Okay, so you can also mention that A consists of 4 different types of hydrogen. Okay, so they are unique types, so we'll give some example over here. Now with some idea, this is just some guesses of the identity, which will not be the definite answer until we go through the entire process. So with this idea, we have mentioned that A has one R group. Okay, and this is where the remaining 4 carbons will be at. It could be arranged like this in a straight chain manner. Okay, and this would tell us that it could have 4 different types of hydrogen in this case. If we were to look at this, I would highlight those that are the same. This hydrogen, it's one type of hydrogen, meaning that any of these 3 highlighted, when it's substituted with a bromine, it would form the same type of same products. Okay, with the same structural formula. Okay, this would form another type. This would form another one, and finally this would form another one. So technically this compound that I've postulated is a possible answer to the identity of A. Okay, I'm just gonna show you one more example. This is not the final answer yet, just to take note, because I need to make sure that it adheres to the remaining clues to the question. Okay, so you can also think about the fact that A, the side chain, I know that there are 4. I can also do some form of permutation as well, where my carbons can be a branch chain on the side chain. The 4th carbon could be somewhere over here. Okay, or it could be something like that as well. Etc, etc. So as long as you do the different branching of the side chain, these are all possible. Let's look at what I have over here as well. Okay, so if I look at the one on the left hand side that I just drew, okay, this hydrogen is one type that would be substituted with a Br. It forms a unique product. Okay, The 3H's on CH3 forms another unique product as well when it's substituted with Br, meaning that it's going to become CH2Br on this blue highlighted portion. Okay, these 2H's would be another unique type. And finally, this will be another unique type. So again, I have 4 different colored hydrogens, meaning that it's going to form 4 different unique products as well. Okay, and the one on the right hand side is just a negative example, but I realized that I forgot to change this, sorry. So it should have 4 carbons on the side chain. So as compared to the one that I've drawn on the left hand side, this is where the CH3, the longest chain will still be 3. The 4th carbon, I attach it instead on the first carbon directly bonded to benzene and shifted it to the right. So it's permutation of the different types of isomers. However, I would realize that there would be less than 4 different types of hydrogens over here, because this 2CH3 is bonded to the same carbon. They would actually form one type of hydrogen. All 6 would form all 6 hydrogens on the 2 methyl groups eventually form the same product, which is where one of the side chain is going to form CH2Br. Okay, this H forms a unique one, and finally these 2H's is another unique one. So in this case, there's only a total of 3 different types of products. It would not be what we want because, again, back to the question, it tells us that A reacts with Br2 in the presence of UV light to form 4 isomeric monobromo compounds. But this one on over here can only form 3 types of bromo compounds. So this would not be a possible structure of A. Okay, so at this point in time, you can also continue to permutate the structures by shortening the carbon chain, but there would be a limit because you would have to make sure that it is fulfills the criteria of 4 different carbons on the side chain. Okay, we shall take a look at that. So far, these 2 on the left hand side are still possible structures, but I'm still not sure which one is the correct one until I follow through all the reactions. Okay, moving on. Okay, the next line says that upon heating with alcoholic NaOH, 2 of the monobromo compounds B and C gave the same compound which can exist as a pair of cis-trans isomers D and E. Okay, so with that, the reagents and conditions of hot alcoholic NaOH, just a reminder, it is where B and C is the alkyl halide, with alcoholic NaOH is undergoing elimination. Okay, so it's going to form alkenes. So D and E contain alkene. Okay, please be clear. You need to mention that which species you are referring to for the specific functional group. And that is also to say that B and C are alkyl halides. Right. So given that D and E's are cis-trans isomers, it would also mean that they would have to fulfill the criteria that it has CC double bond with 2 different groups on it. Okay, and then finally, the last line that it tells us is that when you heat B with aqueous NaOH, it forms compound F, which is a tertiary alcohol, and you need to know how a tertiary alcohol looks like. Okay, so a tertiary alcohol F would look something like that, which you need to fill in accordingly. Okay, a tertiary alcohol would have a OH on a carbon, and the remaining groups over here would have to be alkyl groups, okay, which I do not know the identity. I need to uncover the identity of these R groups later on. Okay, and what we can infer is actually the fact that the reaction that it undergoes is that B undergoes nucleophilic substitution, given that we have already known it's alkyl halide. Okay, to form an alcohol, this is a nucleophilic substitution that we've learned. Okay, F is a tertiary alcohol that does not react with acidified K2Cr2O7. This is what you've learned in hydroxy compounds, which is the fact that F does not undergo oxidation. So that is something that you can deduce as well. So this is actually probably one of the most important information, because it actually helps us to know that the more specific structure of the alkyl halide. And again, back to this, the structure of B actually comes from the identity of how A undergoes free radical sub. So in this case, these two are still possible structures of A, and let's take a look at that. Okay. Right. So in this case, we will look at the structure of F, which I do understand that one of the R group probably would have to consist of a benzene ring. So we will move forward with that to look at whether we can achieve the final answer. So let's quickly look at the first possibility of A. Okay, so if this is correct, okay, if the one on the left hand side is correct, okay, then we'll continue with the postulation to find out whether it will gradually help us know that F is this compound. Okay, so if A undergoes free radical sub with Br2, it's going to form 4 different compounds. So I'm going to draw each of them. Okay, the one in pink, when it's substituted, one of them, this is what you're going to form with free radical substitution. Okay, the one in orange is going to form something similar as well. Okay, so I'm just going to sub in accordingly at the respective position. I will color code it later on. The one in blue, okay, highlighted in blue. And finally, the one highlighted in green. Okay, so these are the 4 different compounds that you would see. So I'm just going to highlight it so that you can see what I'm referring to when the respective hydrogens are being substituted. Okay, and then we'll move on. I need to repeat myself. At this point in time, I'm not sure whether this is correct because it must follow through all the evidence. So let's continue as well. Okay, with these 4 different compounds, I do not know which one is B and C, but it mentioned that out of these 4, if it were to be B and C, they're going to react with elimination and going to form the same compound. 2 out of 4 of this species are going to form the same compound. So I'm just going to look at whether is it possible. So if this were to undergo elimination, the product that would be formed would be something like that. Okay, and let's see whether there are possible products that are exactly the same at this point. Okay, so this one that I've drawn is if I were to remove the Br and H over here. Alternatively, I can also remove the H and Br like this. So let me just draw the other products as well. Okay, then I'll move on. The next one, again, there are 2 permutations. The one in green, let's say I draw this. Okay, and the other one is if I were to draw this. Okay, and finally the last one. There's only one permutation because there's only one adjacent hydrogen. Okay, so this is the 4 different monobromo compounds, and I need to find out if there is a presence of 2 species that is able to form the same compound out of the 4 monobromo compounds. Can I find an identity that's a B and C where they're going to form the same compound eventually? And if you were to look at this, there is one possibility over here, which is this. Okay, these two are exactly the same as you can see. And let's look out for anything else that are the same. Okay, there's another 2 that looks the same as well over here. Okay, maybe I do a different color. So actually out of the 4, there is 2 possibilities that they actually form the same compound. However, in this case, they also mentioned that this same compound must exist as a cis trans, which the one in orange cannot form cis trans. Okay, for the reason that the CC double bond over here has 2 of the same group. Okay, whereas the one highlighted in green, they are still in the run of possibility because they can form cis trans over here. So let's continue. So meaning that could this be B and C that the question wants? Okay, so at this point in time, it is still possible, but again, like I mentioned, it needs to follow through all the evidence. So at this point in time, out of the 4 that I've drawn for the monobromo compounds, only the top 2 could be B and C, and is in the run of finding out the answer. So let's continue. We also know that if it were to be B, it must be able to form tertiary alcohol, which in this case you realize that that is when this postulation of this series of thinking failed at the last point, because if I were to copy this over, okay, if this were to be B, I would realize that when it reacts with NaOH aqueous, it did not form a tertiary alcohol, but instead this is a secondary alcohol. Okay, so this tells us that at this point in time, this cannot be B. All right. Remember, there were 2 possibilities. The one at the bottom can also be B as well, because either one of them is one is a B, one is a C. So let's look at it over here. If this were to be B, okay, when it undergoes nucleophilic sub, okay, that's where the Br is substituted with OH. Okay, in this case, this is still a secondary alcohol. And again, it tells you that this cannot be B. And now we are back to square one. I realized that it started off well, knowing that it's going to form the different structures that we want, which is that it's going to form 4 different mono-bromo compounds, but end up not having the final answer that we want because it failed to fulfill the criteria that F has to be tertiary alcohol.